the aliphatic nucleophilic substitution reactions. So we will continue the nucleophilic substitution reactions. So in the last class we discussed about the Sn1 reaction. So today we will take up Sn2 reactions. Okay, Sn2 reactions. So before taking up this Sn reaction, let us have discuss one reaction type. Suppose in the last say like a bromide or some living groups, butyl groups or some bulky groups are there, the reaction with say nucleophile. So when react this alkyl halides react with the nucleophile, now can undergo this nucleophile can attack from the front side as well as can attack from the back side. So it can undergo but due to the bulky groups, this nucleophile can attack direct from the back side, or it can come to the front side also because the bulky group of the bromide. So in this case we can attack the Sn1 will undergo reactions. First will broken down this one, first will broken down, then we will have this butyl group, bulky groups are here, and then we go to carbocation fast. So first broken down this minus okay, bromide has gone. So it is we are discussing the Sn1 reactions. So bulky groups that nucleophile cannot direct attack from the back side as well as from the front side because of the bulky substituents. So it can attack first from the this carbocation. It is as the substituents are all identical, or this is compound, this is chiral, this is a chiral one. So you can have a chiral, then we can have only one substituent nucleophile, then attack nucleophile, then we have this product. Okay, product nucleophile. I write down here this set key not coming. So you can attack here Br, then carbon, bromide, butyl, and substituents are here, the nucleophile. So this reaction takes place through Sn1 reactions. So this is Sn1 reaction we have discussed in the last class. Okay, that means in this type of cases when the bulky groups are present, then the nucleophile can attack from the front side as well as from the back side. So you can undergo a two steps mechanism. First carbocation is formed and then nucleophile attack the carbocation. It is a chiral compound, so we got only one product. But if this is a chiral compound, suppose it's chiral, all the substances are different, then we have a racemic mixture. Okay, either this nucleophile attack from the back side or front side, so we can have a racemic mixture. So these are all we have discussed in the last class. Suppose let's discuss another one. Okay, so suppose not bulky groups are here, so with all are hydrogen and bromide by nucleophile. So here in this case, when the nucleophile attacks, can attack from the front side because of the bulky bromide group, but it can attack from the back side. So they can attack from the back side, nucleophile can attack from the back side. Okay, so this living group like this. So reaction takes place simultaneously in a concerted mechanism. So here we have hydrogen here, all are methyl groups and nucleophile. So here reaction is a concerted mechanism, and then it is inversion of the configuration takes place. But in the other case, retention takes place, but here inversion takes place. So this is known as Sn2, this one. So I am repeating again that comparing this Sn2, mostly primary methyl and primary some secondary alkyl halides can undergo stable, they do not form stable carbocations. Primary or methyl they cannot alkyl halides, they do not form suitable stable carbocations. So their reactions are with nucleophile must proceed through another mechanism. So I am repeating again here, bulky groups can undergo Sn1 reactions because the carbocation forms are stable. But in the case of methyl or primary alkyl halides, they cannot undergo stable, they do not form stable carbocations like this. They do not form stable carbocations. These are primary carbocations, they do not form. They are less stable as compared to the tertiary carbocation. So they do not form, so they do not attack by the nucleophile, easily, and so they can undergo through another mechanism that is called Sn2 mechanism. Okay, so they didn't go through Sn1 mechanism when the alkyl halides are primary or secondary halides, alkyl halides. The rate of the reactions are bimolecular because the rate of the reaction depends on both these alkyl halide as well as the nucleophile. When the alkyl halide is double, rate of the reaction also double. When the nucleophile is double, concentration of the nucleophile is double, the rate of the reaction is also double. So this is reaction is concerted mechanism. So you can see the rate of the reaction. So I will write down here for Sn2 reactions. So this undergo displacement reactions. So here it's a rate of the reactions is for you can say K2, and it depends on the concentration of both the alkyl halide as well as the nucleophile, concentration of the nucleophile. So it is said to be nucleophile. It's said to be bimolecular, and this is concentration of the nucleophile. Okay. So I am repeating again, this is bimolecular reactions. So the reaction takes place from the back side. Okay. So the reaction rate of the reaction increases when the concentration of alkyl halide increases, and also the rate of the increases when the concentration of nucleophile increases. So the rate of the reaction depends on both the alkyl halide as well as the nucleophile. So this is bimolecular side. So I will repeat some examples I am giving that I have already given. So here say like this, when I am giving one example, okay, from mine, and then we have this. Let's say methyl groups are all methyl groups, hydrogen. Then the reaction with the strong nucleophile, we attack from here, from the back side it attacks on the side, and then leaves simultaneously. So it's all. Then we have this is carbon. Then we have we can have hydrogen here, and then here. Then we have this bromide. Okay, this is the intermediate type. So delta negative to delta positive. You can say delta 2 or delta. So here then simultaneously then finally leaves this the intermediate complex system. Then we have OH, C, and hydrogen here. Then we have hydrogen, then this one. Okay. So here inversion takes place. Inversion of configuration takes place. Inversion of configuration takes place in this case. So here we have inversion of configuration takes place. So just like upside down of these, just as umbrella has a tendency to invert in a windstorm. So just like an umbrella has a tendency to invert in a windstorm for this one. So I am repeating again, the rate of the reaction depends on both the substrate, that is alkyl halide, as well as the nucleophile. When the concentration of alkyl halide is double, then the rate of the reaction is also double. When the concentration of the nucleophile is double, then the rate of the reaction is also double. And the reaction takes place in an inversion configuration, inversion mode. It attacks from the back side because the one side can attack because of the bulky groove, and then inversion takes place to give the only one product. Okay, there is no another product. So this reaction is said to be one-step process and concerted. So this is about the Sn2 reaction. Now let's come to the energy profile or reaction coordinate diagram. Energy profile or reaction coordinate of Sn2 reactions. Energy profile or reaction energy profile diagram, or you can say reaction coordinate diagram. So in this case we have, say like earlier we have energy here, then we have this reaction procedure or reaction coordinate and progress of reactions. We can say reaction coordinate, or you can say progress of the reactions like this. Okay, so here this is a starting with here, then we have this and then lower one, this one is lower, energy level is lower, higher. So we have here, suppose we have CH3 here plus say OH like good nucleophile. Okay, then we have product will be alcohol, ethanol plus HBr. Okay, so this is the, you can say BR. Okay, okay, here then intermediate reaction. Intermediate is the transition state is like earlier one, OH, then C, the hydrogen, then we have this bromide. So we have delta negative, 2 delta positive, or delta 2 positive. Okay, 2 delta 2 positive. So this is the intermediate complex. So it is the intermediate transition state. Okay, so now this is the overall energy profile diagram, or you can say reaction coordinate diagram. So energy diagram is now upon nucleophile attack. When the nucleophile attack to this alkyl halide, only one transition state is formed. This transition state is unlike reaction intermediate. It is not unlike reaction intermediate. It is a very short-lived species. That this transition state is unlike a reaction intermediate. It is a very short-lived species that cannot be isolated or directly observed. So it is, so the overall reaction is a single step, concerted, and forming only one transition state. So here sterically hindered. So one of the features is that sterically hindered reaction cannot reduce the reaction. There are the reactions. If the alkyl halide has many substituents, say let's say R is a more bulkier. If the more bulkier substituents are more bulkier, then the rate of the reaction of the reaction Sn2 reaction is reduced. More bulkier, it comes to the Sn1 reactions. So sterically hindered substrate will reduce the Sn2 reaction. So it favor the Sn1 reaction. Now another feature is that we can have for Sn2 reaction, stereochemical factor. So actually Sn2 reactions are stereospecific. So stereochemical factor here gives only one product, stereochemical factor. So in the case of Sn2 reactions, Sn2 reactions are stereospecific. Sn2 reactions are stereospecific. It gives only one product, unlike the Sn1 reaction, stereospecific. It gives only one product. Okay, so it can attack from only, not from other side. Okay, let's say this is the living group. Okay, then we can have another substance here, then here. Okay, so all are methyl. Let's say methyl. Let's discuss this one, living group. So here nucleophile OH groups. OH. Okay, nucleophile is a strong nucleophile as compared to the Sn1 nucleophile. This is weak nucleophile. In the case of Sn1, nucleophile is weak, but in the case of Sn2, nucleophile is a strong one. So here the reaction comes to the in this case it is only one. Okay, this is a chiral product, a chiral one. So we can discuss similarly. We can have say a chiral one, chiral compound, chiral alkyl halide can also have. So let's say methyl. Another group is ethyl. Okay, ethyl. So in this case also, I think you can see ethyl groups. Okay, I'll write down. Here, you can see. So this is a chiral. This is a chiral. So I will show you another one, chiral one, hydrogen, living group. All the substituents are different. Same methyl groups, and these are ethyl groups. Okay. So in this case of OH groups. So here also same case. Similarly, let's say this is S or R So this you cannot take from the front side because the leading group is bulky. So you cannot take from the back side. So only one, it gives only one product. So it gives only one product. Inversion of the configuration takes place. So you can have OH here, then you have hydrogen, and then you have hydrogen, and this one. Okay, for a chiral, so one product. For chiral also, we can have the substitutions are all different. Hydrogen, methyl, and ethyl. So here also some case it gives only one product. So here hydrogen, and then methyl, and then this is ethyl, then here OH groups. So it gives, if we S will give S, or R will give R. So here inversion takes place. Okay, in this case inversion takes place. Inversion of configuration takes place. So R configuration will give S. R configuration. Suppose this is R configuration, then the product will be S configuration. Or suppose it is S configuration, then product will be R configuration. So it gives only one product is formed with a with the inversion of configuration. So this is about a stereochemical factor as compared to earlier cases. In the Sn1 we got a retention, as well as we have two mixture of components of 10. Okay, the carbocation can be attacked. In the Sn1 carbocation form can be attacked either from the back side or from the front side to give both mixture of the product. Okay, so these are all about the Sn1 and Sn2. Now let's come to Sn mix. Of course, that we can come to mix Sn1 and Sn2 reactions. Mix Sn1 and Sn2 reactions. So let's discuss this. When the reactions of these two types of the reactions, Sn1 as well as Sn2 are mixed together. Sn1 Sn2 reactions. Okay, let's say reaction. So the rate law for the reaction of an alkyl halide that can undergo both Sn1 Sn2 reaction together simultaneously is the sum of the individual laws. So the rate law, I am repeating again, the rate law for the reaction of an alkyl halide that can undergo both Sn1 and Sn2 reactions simultaneously is the sum of the individual laws. Say rate law, so I am writing here again, the rate law for the reaction of an alkyl halide that can undergo both Sn1 and Sn2 reaction simultaneously. That means mix Sn1 and Sn2 reaction simultaneously is the sum of the individual rate laws. That is say for Sn1, say let's say rate is equal to, for Sn1 rate is equal to K1 alkyl halide concentration of alkyl halide. Okay, so I have discussed this one, and this is Sn1. For Sn1, okay, the rate depends on the concentration of alkyl halide. Is independent of this rate of the concentration of the nucleophile. But in the case of Sn2, rate equal to this is bimolecular, so it depends on what concentration of alkyl halide as well as concentration of this nucleophile. Okay, so this is for Sn2. This is for Sn2. Okay, for Sn1, let's say Sn1 this one, Sn2 this one. Okay, rate depends on these different types of reaction. Okay, so I am repeating again, when individually if the reaction takes place for Sn1, the rate depends on concentration of alkyl halide only, But for Sn2, the rate of the reaction depends on both the concentration of alkyl halide as well as the concentration of nucleophile. So if we mix these two together, we mix Sn1, Sn2 reaction, then the rate of the reaction will be combination of these two. So rate of for mix, so I am writing again, for mix Sn1, Sn2 reaction, the rate law is the combination of the two. So rate for Sn1, mix Sn1, Sn2 reaction is equal to K1, the alkyl from the Sn1 reactions, this one concentration of plus K2, so this is mixed, we have to mix together, so it depends on alkyl halide plus, and this on this concentration of nucleophile. Okay, so we have from this one, first one is from the Sn1 and second one is from the Sn2. So for the mix Sn1 Sn2 reaction, the rate law is like this. From the rate law we can see that the increase in the concentration of nucleophile, if the concentration of nucleophile increases, the rate of the Sn2 is increases. From the side is increases there, because here there is no concentration of nucleophile in the case of Sn1. So from this we can say that the increase in the concentration of the nucleophile increases the Sn2 reaction, and there is no effect on the rate of the Sn1. Okay, increase the concentration of the nucleophile has no effect on the concentration of the rate of the Sn1 reaction. Therefore, when both the reactions occur simultaneously, increasing the concentration of the nucleophile increases the fraction of the reaction takes place. So I write down here again. I am writing down here for the mix Sn1, Sn2 reaction. We can see that from the rate law. I am writing here from the rate law. So I'm rubbing this also. Okay, let's see. We can see that an increase in concentration of nucleophile, an increase in the concentration of nucleophile increases the rate of the Sn2 reaction, but has no effect on the rate of concentration of Sn1 reaction. Okay, reaction. So when you increase the concentration of the nucleophile, doesn't have no effect on the Sn1 rate of the Sn1, but increases the rate of Sn2. So therefore, when both the reactions are together, mixed together, when the reaction occur simultaneously, okay, mixed together simultaneously, increasing the concentration of nucleophile. Increases the rate of the fraction of the reaction that takes place by Sn2. Okay, so only Sn2 we increase the concentration of this nucleophile, only the fraction of the reaction takes place by an Sn2 pathway. On the other hand, decreasing the concentration of nucleophile decreases the fraction of the reaction that takes place by Sn2 pathway. Takes place by Sn2 pathway. Okay. So decreasing only the Decreasing the concentration of nucleophile decreases the reaction by Sn2 pathway. So here you can see the Sn2 reaction. But the activity slow step of an Sn1 reaction is the dissolution of the. But in case of Sn1 reaction, if the dissolution of the alkyl halide, dissociation of the alkyl to form the carbocation. If the carbocation electrophile increasing the rate of the reaction does not affect the rate of the nucleophile. So in the case of Sn1 type pathway, for the Sn1 type, the rate of the increase of the reaction of Sn1 does not depend on the concentration of the nucleophile. So whether nucleophile increases or decreases does not affect the Sn1 pathway. So we can say, we can summarize the mix for the mix Sn1, Sn2 reactions. We can summarize Sn. A good nucleophile, their effect favors an Sn2 reaction. A good nucleophile like hydroxy groups, nucleophile favors and Sn2 reaction. Okay, but favors and Sn2 reaction over Sn1 reaction or Sn1 pathway or reaction. Okay, good nucleophile. Whereas a poor nucleophile, like water I discussed earlier, favors Sn1 reaction, not Sn2 reaction, not by increasing the rate of the reaction itself, not by increasing that doesn't affect the rate of the reaction. The rate of the Sn1 reaction, but reaction itself, Sn1 reaction itself is not rate is not increases, but not increases, but by decreasing the rate of the competing Sn2. So I am repeating again this Sn2 the reaction. So if you use the poor nucleophile like water, the sheet favors the Sn1 reaction, but the rate of the reaction increases, but it decreases the rate of the Sn2 reactions. So here, in the case of mixed Sn1 Sn2 reaction, poor nucleophile decreases the rate of the Sn2 reaction, doesn't affect the rate of the Sn1 reaction, and a good nucleophile favors Sn2 reaction over Sn1 reaction. So this is about the high concentration for finally I will wake up. A high concentration of a good nucleophile favors Sn1 reaction. So we have to know, we have for mixed Sn1 Sn2 we have now, and Sn2 reaction is favored by a high concentration of a good nucleophile. Okay, good nucleophile for Sn2, and for Sn1 reactions. For Sn1 reaction is favored by a low concentration. So here is high, here is low concentration of a nucleophile. You can say of a nucleophile, or you can say a poor nucleophile, or a poor nucleophile. Okay, so Sn1s are favored by 4 nucleophile, and whereas the Sn2 reactions are favored by good reactions. That's why for 4 nucleophiles such as water, and the methanols, etc. are used for Sn1, whereas good nucleophiles like hydroxide groups, methoxy groups, methoxide, they are used for Sn2 reactions. Okay, so we have this about the mixed Sn1 Sn2 reactions. Now let's come to another topic, that is Sn1 Sni reactions. So let's have another topic, the Sni, the Sni reactions, that is substitution nucleophilic internal reactions. Okay, substitution nucleophilic internal reaction. So I am here, if in a nucleophilic substitution reactions, a part of the living group attacks the carbon side of the substrate and detaches itself from the rest of the living group, it is known as substitution nucleophilic internal. So I am repeating, I am writing here, if in a nucleophilic substitution reactions, in the nucleophilic substitution reaction, okay, substitution reaction, a part of the living group attacks the carbon side of the substrate and attaches and detaches, remove, or you can say remove or detaches itself, remove itself from the rest of the living group, then it is known as substitution nucleophilic internal, substitution nucleophilic internal. Okay, you can say Sni reaction. Okay, this is also concerted mechanism. So I am repeating again, if in a nucleophilic substitution reaction, a part of the living group attacks and the substrate, a part of the living group attacks the carbon side of the substrate and detaches, removes itself from the rest of the living group, then it is known as substitution nucleophilic internal, Sni reaction. Here the attacking nucleophile has already been present on the substrate and its cell has occurred internally. So living group is a present itself and nucleophile itself is present itself in the substrate cell. The nucleophile itself present in the substrate. So we can have some examples. Best example is the reactions of this reacting with this thionyl chloride SOCl2. Okay, reaction is a thionyl chloride reaction with this alcohol. So we get a substitute, the OH group is substituted by Cl, and we have sulfur dioxide and HCl. Okay, so you can see. So this is one of the best reaction is this one. So here alcohols react in presence of thionyl chloride, gives the OH group is substituted by chloride, then sulfur dioxide and hydrogen. So we can have the mechanism of the reactions of the Sn1 reaction, that the mechanism of the reaction takes place, Sni reaction takes place in 3 steps. Mechanism of the Sni reactions. Okay, mechanism. So it takes in 3 steps. So first step is, so Sn reaction takes in 3 steps. First step is the formation of an alkyl chlorosulfide. So here I write on here alkyl chlorosulfide intermediate size. Okay, reaction with thionyl chloride, Cl. So here this attack here, then we got this one. So formation of this C O S, yes, you can say SO and Cl. You can say O here. No, this coming again, then we'll go this way. Okay, one chloride will go. So you can see this one. Okay, plus HCl. So it is first attack here, sulfur, then leaves, and coming back again and lost this one. Okay, from HCl, the hydrogen combine this one, HCl. This is first step. So formation of alkyl chlorosulfide. This is called, the name of the alkyl chlorosulfide. Sulfide, SITE. Okay, this is the intermediate form. In the second step, this alkyl chlorosulfide intermediate. This intermediate can undergo slowly dissociate into an ion pair. So second step, I write down here, this intermediate alkyl chlorosulfide dissociate slowly into an ion pair and a carbocation. So dissociate. So I'm repeating again this one. This alkyl Cl. Okay, this slow process just to a carbocation, and then like this. So dissociate to a carbocation, and then we have this sulfur dioxide and Cl. Okay, you can write these two together. We can write this way, or you can write here also. You can complete like this. You can keep slow like this, then you can have O S O Cl. Like this starts here. Okay, this same. So here, like this low reluctance given to oxygen. Then we have this one. So here, I'm repeating again this. In the second step, alkyl chlorosulfide dissociates slowly into an carbocation ion pair. These ion pairs are here, positive ion. Another one is this one, ion pair. One is a carbocation. Okay. In the third step, this attacks nucleophile. This chloride nucleophile. This chloride nucleophile attacks this carbocation. Okay. In the third step, so carbocation, we have carbocation. This attacks by this nucleophile. Okay, you can let's see this one. Okay, let's use this nucleophile. O. Okay, I write this way. In the better way, you can write O negative S double bond. Then you have one of this double bond. This O. Then Cl. Okay, this negative charge. So attack here, this sulfur group, this chloride groups, chloride. I think you can see this one. Chloride, okay. So it takes this one coming back, and the chloride attacks here like this. This is this nucleophile, or you can write this way. So we got a chloride attack here. So we got this Cl plus and sulfur dioxide. So this is another one. So here retention of configuration takes place. In this case, I'm repeating again. Okay, this Sn1 reaction mechanism of the Sn1 reaction takes place 3 steps. In the first steps, formation of alkyl chlorosulfide as intermediate takes place. In the second step, this alkyl chlorosulfide dissociates slowly into carbocation and another ion pair, this one. Okay, another ion pair, carbocation, and this one. Then this sulfur, you can write this way, sulfur dioxide loses this one, and chloride loss sulfur dioxide and chloride. This chloride attacks attack here, or this. Okay, you can use this one, or this carbocation attack. In the third step, the nucleophile chloride attacks the carbocation to form the side living group. So retention of here, retention of configuration takes place. So here retention takes place. Retention of configuration takes place. So this is about the mechanism of the Sn1 reaction. So in a concerted way, we can write this one also. You can write in a simple way. You can write. So intermediate first, this intermediate, we got this intermediate. So first, let's say this OH. Okay, this is, let's say this one, and sulfuric thionyl chloride. Yes, say thionyl chloride. You can write this. Yes, so you can write the O is leaving or direct, or you can directly, or let's say the concerted way of this formation of this one. Yes, O, Cl, Cl, S, Cl, Cl, O. Okay. So here, first concerted one we go from earlier one, like earlier cases. We form this one. Is coming back and coming back. Chloride is lost. So we have this O, S. Then we have double bond O. And Cl here. So in a concerted way, you can attack this way or like this. In a this is intermediate. It is intermediate we have discussed earlier. This is alkyl chlorosulfide intermediate. They undergo this like the one in one concerted mechanism. So you can give Cl here. Then we have this one plus this sulfur dioxide. Okay. So this is another mechanism, concerted way. So the rate of the here for the Sn1 reaction is found to be depend on both the alcohol as well as the thionyl chloride. So here the second order kinetics. The rate depends equal to K of this alcohol as well as the concentration of the thionyl chloride, SO2, SOCl2. The thionyl chloride depends on what the concentration of this SOCl2. SOCl2. So here in the case of the Sn1 reaction, the rate of the overall reaction is second order reaction. It depends on the concentration of the alcohol as well as the concentration of the thionyl chloride. Okay, so this is second order kinetics. This is second order kinetics. So bimolecular. So the reaction is here, a retention of configuration takes place. So retention of configuration, second order retention of configuration takes place. Retention of configuration takes place. If we use another important reaction is that when the alcohol reaction takes place in presence of a pyridine as a base, then the reaction takes place with the inversion configuration takes place. So in another way, so reaction Sn1 reaction, the reaction of alcohol with thionyl chloride, if it takes place in presence of a pyridine or a base, then the inversion configuration takes place. So I write that here. Suppose these reactions, so let's say this one, alcohol in presence of thionyl chloride, SOCl2, and presence of pyridine. Okay, pyridine. This is pyridine. Then the reaction takes place in inversion configuration takes place. So here is carbon, then here, then the chloride comes here. So inversion takes place. So just like opposite to that, and when the pyridine presence, base presence, then reaction of this Sn1 reaction takes place. Sn2 reaction takes place in a inverted way. So here I can write the this mechanism of the reaction is as first mechanism of the reaction is that. So this pyridine, all right, write down. Okay, first. So here this organic substrate alcohol then reacts with thionyl chloride. In the earlier case, say O, S, Cl, Cl, like earlier case gives the coming back and lost this chloride. So we got a alkyl chlorosulfide. This we got this C. Okay. Then this O, then S, O, OCl. This is intermediate form. So then plus HCl. This HCl is formed. Okay, these are hydrogen picked up by the chloride. So HCl. This HCl reacts with pyridine. Reacts with pyridine. The HCl. So you got this ion pair. And is positive. Okay, so we got this one. So this the chloride is present here. You can say chloride. This then again we can undergo this. Can undergo this way. They can this. So you have this pyridinium ion. And is positive charge. Then chloride. Okay, this is the chloride. The electronucleophile. This is attached to this. Finally, the final I write down here. This in the last step, this chloride ion attacks to this organic substrate. This CH. So here we have this this thing intermediate OCl. Okay. This one, we have this one. This is alkyl chlorosulfide. Then attacks by this nucleophile attacks from the it attacks from the back side. So you cannot attack from the front side because you cannot attack from the front side because of the bulky groups here. So you attack from this like this, then goes this way. So you can have chlorine, then we have this one. So inversion takes place and sulfur dioxide plus chloride. Okay. So this is the mechanism of the when the pyridine is present, the inversion configuration takes place this way. So we can summarize in the Sn1 reaction without the pyridine, ketone configuration takes place. With pyridine, we have the inversion configuration takes place. So we have different mechanism of these reactions. So now let's compare this Sn1, Sn2 reaction. Okay, now all the nuclear substitution in the case of aliphatic system, we can summarize in the Sn1, Sn2 comparison. Compare this to Sn1, Sn2. Okay, compare these two. In the case of Sn1, it is a two-step mechanism. Sn1 is two-step mechanism, and then here is a one-step mechanism. Okay, this is concerted, and here is a formation of carbocation takes place. So here, first step is the rate determining step. So it is a carbocation is formed. Carbocation rearrangement takes place. Carbocation is formed. No carbocation is formed. Okay, this is concerted mechanism. No carbocation is formed. So then the reactivity rate is that the reactivity rate is here tertiary carbocation reactivity rate. In this case, the rate of here and then tertiary greater than secondary greater than primary or methyl. But here the reactivity rate is just opposite. Okay, methyl just opposite to the this one, Sn1, secondary and tertiary. So reactivity rate of Sn2 like this. Then red law is here. Red law is that red law. We can say red law for Sn1 is that it depends on the only one is the alkyl halide. Okay. So we have seen earlier this. Now we can compare these two. So here in the red, okay, red is equal to this let's say K1, K2. Here alkyl halide as well the nucleophile. Okay, concentration of nucleophile. So I can as well concentration of nucleophile in both alkyl halide as well as nucleophile concentration takes place. So this is about the Sn2, this one and the Sn1. And then in the case of Sn1, so we can have in the case of Sn1 is favored by low concentration of nucleophile, or you can say or by poor nucleophile or a poor nucleophile favors the Sn1 reaction. Here high concentration of nucleophile and or a strong nucleophile. So it is difference between these two, Sn1 and Sn2. You can compare it. So you can see here in the case of Sn1, a tension configuration takes place, or in the case of here a tension configuration or inversion of configuration, inversion. So tension configuration, you can see here a tension. Okay, here inversion takes place. So these are, I am summarizing the between the comparison for Sn1 Sn2. But if the stereochemical factor, if the alkyl halide is a chiral compound, then in the case of Sn1 we got the racemic mixture, but in the case of Sn2 we got only one compound in inversion configuration. That is, for stereochemical factor, in the stereochemical factor Sn1 racemic mixture, but in the case of Sn2 is a state specific. It gives only one product. So R will give S, in the case of R will give S will give the R configuration in the Sn2. But in the case of Sn1, R will give S in the R mixture, R will give S in the R mixture. Okay. So it is like for chiral alkyl halides. So these are about the nucleophilic substitution for alkyl aliphatic system. So we have discussed so far. So next class we will do the electrophilic substitution reaction. Okay. Today we will wind up here.